Hi and welcome to Module 6, Acid and Base Reactions, and today we are looking at calculating the pH, the pOH, H plus ions and OH ions, or concentration of those ions in solution. So before we start, we'll just recap some of those things we were looking at today. So in our class, or in our last lesson, we were looking at measuring the pH of a variety of different household solutions using a pH meter and also a universal indicator. And we talked about the relationship between the pH and the concentration of those hydrogen ions in that prac that we did today. And you can see down the right hand side in this table some of those substances that you may have tested in today's lesson. For example, our household ammonia having a pH of around about 11, our pure water, so our distilled water, about that 7, and some of you being interested in the battery acid that had a pH of 0. And you can see on the left hand side of our table here we have the concentration of our hydrogen ions. And if you can see moving down the table there, you can see that their concentration is increasing by a factor of 10, and from the bottom up decreasing by a factor of 10. And that's because our pH scale, as we may have mentioned before, is a logarithmic scale. So rather than a linear scale, it's a logarithmic scale increasing by that factor of 10. So each increase in pH is actually an increase tenfold in its concentration. So looking at this example is an example using water to start with, our neutral solution. So at 25 degrees, our water and our hydroxide ions are actually equal. If we look at this equation just here on the right hand side, we can see that water, as we discussed in class, can either donate or accept protons. So in this case here, my water can donate a hydrogen to my other water molecule. And in this reversible reaction, we will find that one will become the hydroxide ion, having lost the proton there, and the other one will become the hydronium ion, where it has gained that that hydrogen, sorry. So you can see that if we were to look at the ratios there, they're all in a 1-to-1 ratio. So the concentration of our OH is going to be equal to that of our H3O+. So when we work this out, they're both equal. So our OH and our hydroxide ions are equal, both coming in at 10 to the minus 7, because 14 is our highest pH that we have. So the pH and the pOH add together to give that 14, so therefore the pH therefore must be 7. So how do we calculate this pH? There is a formula that we do use, and it's here on our screen in green. The pH is equal to the negative log of the hydronium ions in solution. So that pH scale has been made to measure that acidity, and using this formula we can calculate not only the pH in solution, but if we're given the pH we can calculate the concentration of those hydrogen or hydronium ions. So what's actually happening is, as my hydrogen ions increase, we're actually going to find that my pH actually decreases. So from this formula, we can actually rearrange it. If you're any good with your logs, we can actually rearrange that equation and find out that if we want to calculate the hydrogen ions, it's actually 10 to the negative power of the pH. So for example, if I've got hydrogen ions, say for example I've got a 0.1 molar solution, that is 10 to the minus 1. This is pretty simple and we don't need a calculator. 10 to the minus 1, the pH is 1. In the next example, 0.01 molar, our concentration is 10 to the minus 2, so therefore our pH is 2. But it's not always so simple. So let's look at another example that we've got here. Say for example my hydrogen ions is 2 times 10 to the minus 5, and I want to calculate the pH. Now I am going to need my calculator. And again, the formula, pH is equal to minus log to the base 10, and the concentration times by the concentration of those hydrogen ions. So inputting that into our calculator, minus log using your base 10 function, 2.0 times 10 to the minus 5. It's probably useful to use your brackets here just to avoid any calculator error, and your calculator should give you 4.7. I'd suggest you give that a try now just to make sure that we've got the nitty-gritty of the calculator skills sorted, so that's not a problem and a cause of error. Give that a go and check that that's the case. If it's not, we'll talk about that in class tomorrow. So let's look at the reverse now. We've calculated pH knowing the hydrogen ion concentration, but what about actually calculating the hydrogen ion concentration when we know the pH? So today in class, we measured a whole host of substances and measured their pH. So from that, we can actually calculate their hydrogen ion concentration. So for example, that formula again, concentration of hydrogen ions is equal to 10 to the negative pH. So in this case, our pH is 8.5, so it's 10 to the power of negative 8.5, and we get a hydrogen ion concentration of 3.2 times 10 to the minus 19. So what I'm going to ask you to do now is have a go at these 4 questions that I've got here on the bottom of the screen. They're using some of those examples that I have just used on previous pages, so go back if you need to. I will record a video and we will watch that on POH for our next lesson. We'll do some more practices in class. See you later.